All right. So at this point, we understand the structure of the heap. Next, so because our goal, our plan, we need to do the heap sort. And we also need to do the analysis for the heap sort. Because at the beginning, in the introduction part, we said we want to find a sorting algorithm that satisfies several special requirements. So we need to, get those requirements in the heap sort. So this part, we need to do some preparation, mainly for the analysis part. Later, so when we try to calculate the cost function for the efficiency, we need to use the result from this part. All right. First, let's look at this small topic, number of leaves in a heap. First, let us use formulas to describe leaves. All right. First, given a heap, we know what are the leaves, right? So these are the leaves. Leaves. Those nodes without child nodes. All right. So we understand the meaning, but next thing is, how do we use formula to represent leaves? Yeah. So we need to look at the parent-child relationship. So in the heap structure, when we build a binary tree inside a heap, we use this relationship. If the parent node corresponds to A of I, then child, so here, one of left. So this one corresponds to left child. Okay? Not right child. Right child, 2i plus 1, right? Yeah. But here it is better to use the left child representation, not right child representation. Why? The answer is easy. Look at this example. This node has a left child but no right child. So based on our observation, if a node is not a leaf, then it must have a left child node. So we use that observation. Okay? Yep. Because if a node is not a leaf, it may not have a right child for this case, as a special example. Yeah. All right. So based on that, so we use that relationship. Now, what is the meaning of no child? Because for a leaf, there is no child. What's the meaning? So here the meaning, we mean in formula. Can we use a formula to represent? Yeah, that's what we need. Yeah. So if no child, let's look at the index to I here. If this parent node, this node corresponds, if this node, let's say A of I has no child, what's the meaning? So this does not exist in the heap. Or in other words, we can say the index to I is out of bound. If it is out of bound, you cannot find it in the heap. That means it does not exist. Yeah. So this is our interpretation, out-of-bound interpretation. Okay. All right. So now let's look at the condition. Out-of-bound. So what do you mean out-of-bound? So we want to represent it, this out-of-bound requirement. All right. I within the bound. So I less than or equal to n, but 2i is out of bound. N is the bound, right? N is the bound. So out of bound. So that's the meaning of out of bound. Yeah. We know the index either range between 1 and n. And we do not use 0. Remember, we do not use 0 for a heap. Yeah. Now we can get divided by 2. This inequality divided by 2, we have n over 2 less than I. Strictly less than I. Okay? All right. But the I must be an integer. So the question is, what is the minimum, the smallest integer for I that satisfies this condition? Smallest integer that satisfies this inequality. That's very easy. The smallest such I, floor function n over 2 plus 1. We have this plus 1. Smallest such I. Remember, the I should be strictly greater than n over 2. So that's why we use this plus I. Okay? All right. So now we can clearly represent the range for those i's such that they correspond to leaves. This range. Okay? The smallest possible, the largest possible. All right. So now we can answer the question. What is the number of leaves in a heap? Number of leaves in a heap. We need to do the counting. How many i's in this range? How many i's in this range? Okay. All right. So to count that, so here I hope you can count carefully. All right. The largest possible I, the smallest, but if you want to calculate the total number of elements in this range, you need to use the largest one, subtract the one before the smallest one, not the smallest one. If you subtract the smallest one, you subtract the smallest element away. We don't want to do that. So you want to subtract the one before the smallest element. So that's why the answer is, if we write, the answer is n minus floor function of n over 2. Yes, that's the answer. Yeah, so our first answer. All right. All right, but this formula can be further simplified to this one-term expression. Can be simplified. Okay? So the two-term expression can be simplified to one-term expression like this. Yeah. We use this formula. This formula on page of the textbook 477 appendix. So we have that, formula appendix. Yeah. So you can find it easily. If you want to prove it, you can also prove it. Yeah. So later I will talk about the proof of equality or inequalities like this. Yeah. All right. Next, number of internal nodes with height 1. So when we're going to study more, after leaves, we want to look at all other nodes with a given height. Remember the title of this part B.1. Number of nodes with given height in a heap. We want to do that for this part. Yeah. So, but we go one step forward. We want to look at number of all internal nodes. All. That's easy. Yeah. After we get the answer from the previous page, so this step is pretty easy. Yeah. All right, so look at this. This is an example heap. Yeah. Now we want to look at the, number of internal nodes first, all internal nodes first. The total nodes given n, and we also know the number of leaves n minus floor function of n over 2. Now the difference part, number of internal nodes. Yeah. That's an easy answer. So that is the floor function of n over 2. Yeah. All right. But the next, we want to look at this. Number of internals with height 1. Only height 1. What is that formula? Okay. All right. Look at those nodes. These two nodes with height 1. Okay? Because there is one edge. Yeah. And this node also height 1. One edge here. Okay? All right. But for a general heap, how do we use a formula to represent the number of nodes with height 1? Okay? All right. Yeah. How do we describe those nodes? Their children are leaves. How do we describe those with height 1? We use this statement. Their children are leaves. How many nodes satisfy this condition? Okay, yeah. Let's use this formula. 2i left child expression, right? 2i left child expression. This position must correspond to a leaf position. A leaf has a position. Yeah. That means this position should be in this range. Yeah. So that's the expression for these internal nodes. Okay. All right. So now let's do division. Division by 2 and try to simplify it. We get this formula. Okay. Yeah. All right. How do you see this? Can you understand this formula? How do we get it? Yeah. This part is easy, right? So divided by 2, then take the floor function. So the right inequality is easy to understand. But how do you understand the left inequality? That is not that obvious. Yeah. So here I want to help you understand the left inequality. Yeah. To derive the left inequality, we need to use this formula, identity. Yeah. This formula. Yeah. How do you prove this? How do you know this is correct? Because in our appendix section, we cannot find it. Yeah. We cannot find this formula in our appendix section. Yeah. So if you want to prove it, but we can prove it. If you want to prove it, here, let me tell you the method we use to prove it. Okay. We do discussion. Look at the denominator here, 4, right? 2 squared, that's 4. All right. N integer. Let's divide it n into these categories. First, multiple of 4, 4k. Second, 4k plus 1. Then 4k plus 2. Then 4k plus 3. Okay? So for each category, so you verify this formula is correct. Yeah. You verify each one. The calculation is pretty easy. Yeah, so you can verify it easily. Yeah. After that, you prove it's correct, then you apply it here, simplify it, so you can get this formula. Okay, all right. So with this formula, next we use the same way we used in the previous slide. You can get the formula for the number of internal nodes with height 1. This number minus the index of the one before this position, before that. Okay, so that's this representation. Okay, yeah, that's all right. Next, we may like to simplify this formula a little bit, yeah, because for the leaf, when we get this formula, we simplify it. After we get this one, can we simplify it from two-term expression to one-term expression? How about that? Yeah. All right. So remember, we have this formula, right? So we have this formula. Okay. But in this formula, n is an integer. Is an integer. Okay. But here, n divided by 4, n over 2, n over 4. This n over 2, not necessarily an integer. That means we cannot apply this formula directly. Okay? Yeah? Because the condition is different. Yeah. But we have another formula. We can use inequality. So here, less than or equal to this one. Not exactly equal. Yeah, because here it's exactly equal. Yeah. Here that is m minus n over 2 floor function exactly equal ceiling function n over 2. But here n over 2, it is not an integer like m. Could have a fractional part, right? Yeah, but for that situation, this becomes inequality. Yeah. How do we prove that? Right? Yeah, because that formula, if you want to understand it, you may like to prove it. Right? So we can prove this formula. This is the formula we use. How to prove it? The same way as we used here. Okay? So you can discuss n in the 4 different categories: 4k, 4k plus 1, 4k plus 2, 4k plus 3. So you can easily verify this formula for those n. Okay? Yeah. Easily. Yeah. So here I'm gonna repeat that part. Okay? Yeah. Now we have this formula. Right. For this part, we have that. That's the equal one. Yeah. Then for other, we use inequalities. Okay. All right. Now we want to generalize the formula to any height. Any height. And not just one. So 1, 2, 3, 4, any height. Yeah. The formula is pretty straightforward. Yeah. So we can, do some simple extension easily. All right. Generalize the previous result. Number of leaves. Leaves means height 0. Okay? Yeah. Number of nodes equal ceiling function of n over 2. Number of nodes with height 1. Okay? Less than or equal this time. Okay? All right. Yeah. Then generalization. Okay. So change to 2. We increase the exponent number by 1. Okay. Yeah. Here it is 1, right? So 0. Here is 1. 1. Here is 2. Okay. 2. It's 3. Okay. One more. Then the height number. Okay. The height number h plus 1. That easy generalization. Yeah. But if you really want to derive it, yeah, so here it looks like you guess the result. But if you really want to derive it, you can derive it easily. Yeah. You just need to prove this inequality when you derive it. Yeah. All right. But when you prove this inequality, you can use the discussion. N equals 2HQ quotient plus R. Okay? This R you can discuss. 0, 1, 2H plus 1. Okay? 2H plus 1 minus 1. Okay? Yeah, although many numbers, but you can look at the R. You can mainly look at R less than or equal to 2H, or R greater than 2 to the H less than or equal to 2 to the H plus 1 minus 1. Okay, only discuss these two different cases, so you can prove that. Okay, all right. Anyway, so the proof is not that hard. Okay, yeah, not that hard. So we have this inequality. Then apply max heapify at a node of height h. The cost is big O of h. Yeah. You can see that easily. Yeah. So how do you see that? Max heapify. Yeah. Recall the heapify operation we did last time. Yeah. Suppose we do heapify on this node. Okay? Yeah. Okay? Going down. Remember? Going down. Okay? Suppose the height is h. Okay. All right. So then when we do max heapify, we move down, heapify down, heapify until we reach a leaf. Okay? Yeah. So that's why how many steps you go. Each step you do big O of 1 operation, the cost function big O of 1, but you go h steps. H steps. That's why you get big O of h. Yeah. Next, cost of max heapify for all nodes of height h. Yeah. You just count the number of nodes with this height. You do multiplication. So that expression is this. Because the number of nodes expression, based on what we get here, less than or equal to, so we get an upper bound. Right? We have this upper bound for the cost of max heapify all nodes of height h. Okay? All right. So after this, we have the preparation for our next level analysis. Yeah. So we will do some preparation before we can do the analysis to get the total cost for the heap sort. All right, so we complete part B.1.